So today's video is on hydrogen halides. So first, hydrogen halides. And a hydrogen halide is composed of a halogen and a hydrogen. This is pretty self-explanatory. And the ones we're going to be looking at in more detail are hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. So first we're going to look at how sodium halides react with sulfuric acid. And the importance of this is that we can make some hydrogen halides by reacting sodium halides with our concentrated sulfuric acid. And for example, sodium chloride reacts with sulfuric acid to produce our hydrogen chloride. And this reacting sodium halides with sulfuric acids works with chlorine and fluorine. So sodium chloride and sodium fluoride can react with our concentrated sulfuric acid to get our hydrogen halides. And this is because chlorine and fluorine have a higher oxidative power than our sulfuric acid. And for quick reminders, oxidative power is just how strongly the atom attracts electrons. And this is why sodium, bromide and iodide will not react with concentrated sulfuric acid to create our hydrogen halides. And this is because our sodium, bromide and iodide have a lower oxidative power than our sulfuric acid, so we'll lose electrons to our sulfuric acid and hence forming their natural states. For example, our bromide ions in our starting sodium halide will lose electrons to our sulfuric acid, hence forming bromine. And this means that it will not go on to form our hydrogen halide like our sodium chloride and fluoride will. And next we're going to be looking at stability. And thermal stability is just how easily things break apart under heat. And so our hydrogen fluoride and hydrogen chloride are actually very stable thermally. And this means that they will not split into hydrogen and halide ions when they are heated. But hydrogen bromide and hydrogen iodide are less stable. And this is because hydrogen bromide splits slightly into its hydrogen and halide ions when put under heat, and hydrogen iodide splits even more than hydrogen bromide. But why does the stability seem to decrease down the group? And this is all because of bond enthalpies. And as you can see in this table here, the bond enthalpy seems to be going down, our bond enthalpy of our hydrogen halide bonds. And this decreases our stability. And this is because as we go down group 7, so from fluorine to chlorine to bromine to iodine, our atomic and ionic radiuses increase. And this is because we're increasing the amount of energy levels. So as we go down the group, we're increasing the number of energy levels, hence increasing our radius. And as we increase the radius, we're increasing electron shielding. And shielding is when the electrons closer to the nucleus shield some of the nuclear attraction from the electrons further out. And as we increase the radius, we're also increasing the distance from the nucleus. So this decreases our nuclear attraction altogether. And this increase of shielding, our increasing distance, decreasing our nuclear attraction, all helps to weaken the bond enthalpy as you go down the group. And this weaker bond enthalpy means that less heat energy is required to break the bond, hence the stability decreases. So hydrogen iodide has the lowest bond enthalpy, so will require less heat energy to break the bond. And this is because iodine has the largest atomic and ionic radius, because of increasing energy levels. And next we're going to be looking at acidity. And hydrogen halides are strong acids. And this is because they dissociate in water to produce hydrogen ions. And to dissociate just means to dissolve in water. So if we look at an equation, we have our hydrogen chloride, and it is aqueous because it's dissolved in water. And this produces hydrogen ions and chlorine ions. And if we think about these hydrogen ions that are being produced and we link it to the pH scale, as hydrogen ions are being produced, the concentration of hydrogen ions increases. And as you increase hydrogen ion concentration, you go further down the pH scale into the acid section. So it makes sense that as we dissolve our hydrogen halides in water, producing hydrogen ions, we will go into the acidic part of the pH scale. And so hence these become strong acids. But hydrogen fluoride is an exception to this rule because it only partially dissociates in water. So this makes it a weak acid. So whereas the other hydrogen halides will dissolve fully in water, producing loads of hydrogen ions, hydrogen fluoride will only partially dissociate, creating less hydrogen ions, so will be less acidic. It will be less far down the pH scale. And then we come on to reactions with ammonia, and ammonia is a base, and you can see here the formula for ammonia. And because ammonia is a base, this means that it will accept protons to become ammonium ions. And these ammonium ions can react with our halogens. For example, ammonia will react with our hydrogen fluoride to create ammonium fluoride. So this ammonium halides that we form reacting with our ammonia and our halogen. And then finally we're going to look at reactions with sulfuric acids and hydrogen halides. And hydrogen bromide and hydrogen iodide will react with our sulfuric acid because they have a lower oxidizing power than our sulfuric acid, whereas chlorine and fluorine have a higher oxidative power than our sulfuric acid. And as you can see here are our equations for our hydrogen bromide and hydrogen iodide reacting with our sulfuric acid. And because our bromine and iodine have lower oxidative powers, this means that the sulfuric acid can actually take these electrons from our hydrogen halides, forming their natural states of bromine and iodine. And as we said before, oxidizing power is just how strongly the atom attracts electrons. But it is actually the difference in our oxidizing powers that affect how much sulfur is reduced. And being reduced just means it gains electrons. So if we look at hydrogen bromide, this reaction, sulfur starts off with a +6 oxidative state, and it is reduced to a +4 oxidative state in our sodium dioxide. And this isn't a massive difference between our oxidative states before and after the reaction, and this is because bromine and our sulfuric acid actually have quite similar oxidative powers. Even though sulfuric acid does indeed have a higher oxidative power, it's not much higher, so sulfur isn't reduced as much. Whereas in our hydrogen iodide reaction, sulfur goes from a +6 oxidative state to a -2 oxidative state. And this is because our iodine has quite considerably less oxidative power than our sulfuric acid. And because of this larger difference in oxidizing power, sulfur is reduced much more than in the bromine reaction.